Good morning, all of you. We are going to start the session within 2 minutes. So, hope at present there are 30 participants have joined in this meeting, and we are going to start the FDP.
Okay.
आवाज किसकी आ रही है? हेलो सर, प्रिंसिपल मैम आएंगी कि मुझे स्किप करना है फिर?
नहीं, वो मैं उन्होंने बोला है कि 11:40 को कॉल करेंगे।
अच्छा,
तो पहले आप डन करो,
ठीक,
उसके बाद कॉल करेंगे।
ठीक है, उसके बाद आपको मैं इनवाइट करता हूँ। बेटा आप लोग अपना माइक स्पीकर थोड़ा सा एकदम आवाज़ कम रखना, नहीं तो So I welcome you all. I welcome you all in the 5-day online FDP on titled Flow Characteristics and Turbulence Statistics in the Alluvial Channel, which is going to start from 6 December to till 10 December 2021. And we are going to start our function with the prayer, so Saraswati Vandana. So I am going to share. So welcome again to all of you in the Atal sponsored and organized by Civil Engineering Department LDC 1 week online FDP on flow characteristics and turbulence statistic in alluvial channel from 6 to 10 December 2021. So here we have joined for the inaugural ceremony, and the patron and for this course is our respected principal ma'am Rajul Gajjar ma'am. And as a convener, we have a Dr. Arbik Khasia sir today. He is the professor and head of Civil Engineering Department. And as a coordinator, we have Rajesh Jain sir and my colleague Utkarsh Nigam sir and myself Sudhanshu Dikshit are coordinating this 5-day FDP. So now I am inviting respected Dr. Arbik Khasia sir for the welcome about the department and the institute. So
thank you, Sudhanshu. Can you hear me, Sudhanshu?
yes, sir. You are audible, sir.
I, Dr. R.B. Khasia, Head of Civil Engineering Department, welcome you all on behalf of the Civil Engineering Department. Dalbat College of Engineering, LDC, Ahmedabad is a premium government engineering institute in Gujarat state, set with the objective of imparting higher education, research, and training in various fields of engineering and technology. The institute was established in June 1948. The institute is affiliated to Gujarat Technological University, Ahmedabad, and administered by Director of Technical Education, Government of Gujarat. There are 14 departments with UG and PG courses. Currently, every academic department has its own significant number of PhD scholars and substantial amount of research work is going on. Civil engineering department is one of the oldest department and is accredited from NBA in 2019. There are UG course, PDDC and 2 PG courses running under civil engineering department. There are 23 faculties with various expertise fields like water resource engineering, transportation engineering, environment engineering, etc. The department is enriched with doctorate degree faculties. We have well-equipped labs with enriched infrastructure. More than 10 projects are going on related to startup and innovations. Research project and publications give strength to the department. With this brief about department, I would like to welcome you all in the 5 days online FDP organized by our department and sponsored by Adult Academic AICT. Hope you will learn a lot of during this FDP program. Thank you all.
Thank you so much, sir, for your kind words and continuous support for this 5 days FDP. We are very thankful to you so that you have given your precious time for this FDP, being very busy now these days. So thank you once again, Khasya sir.
Thank you so much.
So we are waiting for our principal ma'am. She is about to join. Till that, we will have a brief introduction about the training by Dr. R.K. Jain sir, Professor in Civil Engineering Department and the course coordinator, main mind maker for this 5-day FDP. So I would like to welcome Dr. Rajesh Jain sir for this for the kind words. Yes.
Yes, thank you, Sudhanshu. Am I audible?
Yes, sir.
Yes. So, on the behalf of Civil Engineering Department, LD College of Engineering, I welcome all the participants in this 1 week short-term training program on flow characteristics and turbulence statistics and LEV channel. This topic, you will feel that probably a new one, which you would have not studied during your undergraduate program or as well as in postgraduate program. This topic usually studied in PhD program, and few institutes do have instruments which can gather these data to study flow characteristics. During this 1 week, we would like to explain you, make you learn about this turbulence characteristics word, what we measure in this turbulence characteristics, what we calculate in this turbulence characteristics or flow field analysis. Our aim is to make you aware, to make you, I should say, learn about these things, where we would be discussing about measurement of turbulence data, quadrant analysis, flow behavior in scour around piers, scour around spur dike, near-bed particle motions. Also, 2 lectures, 2 sessions from Dr. Ramesh we have. And at the end, we do have one lecture on this human conscience and meditation, which is nowadays made compulsory by AICT as one session. So we will have one session on that, either health, happiness, or meditation. That we will also have a lecture on Friday. So in a nutshell, our aim would be that you are competent enough to do the calculations in the field of turbulence characteristics. See, when we have heard about the word turbulent flow only, we know that turbulent flow is there when Reynolds number exceeds some limit, the flow becomes turbulent, or flow in reverse during flood is going to be turbulent. But what are its component parts and how they are calculated? At least we would be able to explain you, we would be able
Hey,
to
what
make you
I'm
learn,
getting,
and its
the
application
same
in the
my
fluid
voice is
hydraulics,
reflecting to me.
or maybe
My voice,
in
when
the
I'm
field
saying
of
something,
river engineering,
it's coming to
mobile
me
gas
also.
channel, that would be our target. One more thing I would like to speak here, that as AICT has made attendance compulsory for award of certificates, so I request, urge, even warn you
Is it
that
mobile?
you should
No,
all should remain
when is
present.
I'm talking with you,
80%
there is
attendance is
something like if I
compulsory
go and
to
it is a
certificate,
same thing is coming to
and
me
we will
second
make
time, it
that
is echo. It's one kind of
sessions
echo.
interactive. We
Yeah.
will try to make the sessions interactive, but your cooperation is highly appreciated. You should not be like that, just joining and not responding whenever it is called or whenever we want to interact you. So it will not be good as a learner. You all are faculty members from various institutes. Students maybe from Gujarat or outside the Gujarat, you should be very attentive and learn whatever we are going to discuss, and it will make me happy as well as our speakers happy, so that is also required. So with this, just a suggestion, I would like to welcome you again in this training program, and I hope that you will enjoy this online training program for the 5 days. Thank you.
Now? Oh, now too much sound is coming. Too much sound. Okay, let's see what happens.
Thank you, Jen sir, for brief introduction about the training program. So we are about to start our session. Let me check. So at present we have 41 participants joined this meeting. So I think ma'am has not joined the FDP as she is very busy in the another function in the that is going to organize in the month of January 2022 Gujarat Vibrant and Conference. So now I am on the behalf of Civil Engineering Department going to give the vote of thanks. So I myself, Sudhanshu Dikshit, co-coordinator of this FDP, taking this opportunity to propose the vote of thanks to you all. I am on the behalf of the coordinator team, bowing to Almighty God for bless us to the good preparation and arrangement of the program. I am we are very much thankful to the respected principal ma'am, Raju ma'am, for her guidance, support and encouragement. I am thankful to the head civil engineering department, Dr. Abhi Khasya sir, to encourage us to propose and plan this for this Atal FDP in the month of December 2021. His constant motivation, guidance and support have shown this special day. And I am also thankful to the AICT, Atal Training and Learning Academy, Ministry of Education, Government of India, New Delhi, for supporting, sponsoring, and sanctioning the fund for this online FDP. I am thankful to the CT Gandhinagar TNA portal, OSD Dr. Ragesh Kapadia sir, for uploading the HTTP brochure, office order of the government degree and diploma faculties interested to participate for this FDP. I am thankful to Dr. B.S. Mujumdar sir, Professor ISI Kolkata. He is also joined here. I am thankful to Dr. Rajesh Jain sir, coordinator of this FDP, and other senior professors of our department. I am thankful to the account officer, Shri Momtara, for his guidance and support in the financial matter. I am thankful to the faculty, all the faculty members of Civil Engineering Department for cooperation and as and when required for this preparation of this FDP. I am thankful to my colleague coordinator, Professor Utkarsh Nigam, of our internal cooperation, arrangement and preparation for this FDP. I am thankful to all the experts of the FDP to accept our invitation and inputs for the FDP. I am thankful to the participants, to all of you from various colleges, states of India for their motivation in the learning and timely registration for this event. I am also thankful to the students who are continue in this work. And if I forgot to propose the thanks, please pardon all who have directly or indirectly helped us in the preparation of this FDP work. So thank you all for registering for this FDP, and we are going to start the session within 5 minutes. Okay, for the keynote address by Dr. B.S. Majumdar sir. Okay, so we will again start within 5 minutes. Get connected.
Hello. Yes, yes, please. I can speak. Hello, you are from. Can you hear me?
Yes, sir.
But
You are.
one thing is coming echo is coming to me.
No,
My
no,
words is coming. My words are coming to me.
now it is coming. Echo is there.
Echo is coming. Yeah. Number of times.
So,
echoing.
have you? Are you using your headphones, sir? No.
No, no, I am not using headphone. It's a sound and echo too much.
Are you logging on two devices? Majumdar sir?
Can you hear
Yes,
me?
sir. I think sir has using two devices.
Maybe something problem.
So use only one device.
Uh-huh. Oh, it is too much echo, too much echo. I cannot say anything. Why it is coming like that?
Sir, your two accounts are showing as a guest. So in I think in laptop also either you have joined in two different browser or anything else. You can check.
Hello?
Sir, sir,
Yes. Yes.
what I am saying, have you
No, login means I do not have the number of you are sending also there. I was working. Laptop. Not in mobile. I cannot start in the, but I can do the on laptop. Should I log out from the computer completely? Okay. Let me see.
Yes, sir. Now it is, sir, completely. So today we are having three sessions. First one is Keynote Address by B.S. Mujumdar sir. He is joining. And then we have a second lecture from 1:30 to 3, Turbulence Characteristics by Dr. Rajesh Jain sir. And third lecture starting from 3:30, Measurement of Turbulence Data by ADV. And all the lectures are followed by question and answer sessions. If you have any doubt, any query, then you can ask at the last of the session. And we are also going to create the list of question answers so that we can if not possible at that time, then you will get your answer later also through mail. So we have a very good sessions scheduled in this entire FDP. So Majumdar sir is joining.
Okay, can you see me?
Yes, sir. Yes, sir.
What about my words? This is not coming also now echo.
Clear, sir. Clear.
Okay, let's see. Okay.
Now you can share your screen, sir.
Huh? Share on screen. Okay. I have to talk something little bit more before. Okay. Share on screen. Okay. The screen share, should I now click on sharing? Now it has come screen share. Should I click there also? Okay, desktop. Okay. Then where should I go? It has come in a small screen.
Below screen, sir, you have to click.
Okay, where should I click? Okay, share. That's in the okay, share. Okay, no, it is not coming. Wait. Screen. It was coming, no problem. But now why is computer screen? Yes, I say yes. Now you see here. Rajesh join. I can see. I cannot see, but
Yes, sir. It is shared now.
It is shared now.
Yes, sir. Now you can.
But I cannot see now. I can see you, one fellow, Dikshit. But can you see me? No. Camera. Okay. Wait. Video camera. Yeah. Now it is. Is it on now?
Sudhanshu, screen is visible?
Complete screen is not visible. Half screen.
Sir, your screen is visible to us.
Screen is visible to you? But,
Yes.
but you see video, but mute, it is not mute, but in the video it is cross. Why it is not coming? Can you see me? Can you talk? Can I talk? Can you hear me?
Yeah,
Yes.
completely audible, sir. Completely audible.
Yes, sir, we are able.
Okay. Then
Completely audible.
when I start something, stop sharing. Should I go stop sharing? This is also there. Team microscope is sharing your screen. Okay. Then okay. What I can do now? But
See,
video.
sir, again unshare it and share it just once.
Again unshare.
Yeah, cross.
Where should I cross? Here?
Yeah.
Stop sharing.
Yes,
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 stop
stop
sharing.
Yes,
Okay. Open share tray. Again, should I go?
yes.
Okay, open share tray. Okay. Now, screen share. Screen share, should I? Huh.
किसी और ने भी अपनी screen share.
Okay. Screen share. It is come. Same thing is coming. Same. These are. No, should I go to window?
Yes, Windows. Select window and then share.
Okay. Window. No, it is not coming. Share. No. Entire screen. Can you?
Please select entire screen.
Entire
All the
screen.
participants are requested not to share their screens.
But the entire screen, should I share? Should the entire screen have click?
Yes, sir. Yes, sir.
But
Yes, sir.
entire
You
screen
share
is not.
entire screen and then open PPT.
Oh, should I? But I want to say something first before PPT.
Okay.
Okay. Okay. Should I open the share? Okay. Can I open the PPT? Okay. Now it is open. Can you see? Can you see the PPT?
No, sir, it is not shared, sir. Your screen is not shared still.
Oh, why it is not like same thing is coming? Share. But in the share, it is not coming anything. Window, but entire share I have clicked, then share also bottom share is there. That is not blink, that is not colored, that is the dead share. Like I cannot do anything. It's not coming hand. And then can you hear me?
Yes,
Hello?
sir, you are here completely audible.
Then no problem, I can start.
Yes, sir. Before starting, let me give you a brief introduction of you.
Okay, sure. You
Yes,
introduction,
yes.
give the introduction. I will start. I will just talk, no problem with you people. Then but he cannot see my PPT also. Okay, I will talk, no problem. Hello. Okay. Okay, sure. Oh, that's good.
Sudhanshu?
Yes.
Sudhanshu?
Yes, sir.
अभी इनका आप शुरू कर दो सर का.
Yes, I'm going to. So for the keynote address, we have Dr. Bijoy S. Mujumdar sir with us. He is the former professor and head of the Physics and Applied Mathematics Unit, former in charge of Fluid Mechanics Laboratory, ISI, Calcutta, and UGC Emeritus Fellow from 2014 to 2016, and visiting professor in the Hydraulics and Fluid Mechanics Laboratory Department of Civil Engineering, IIT Bombay. And sir is mainly dealing with the applied mathematics, experimental fluid mechanics, and area of interest is applied fluid mechanics related to turbulence, particle fluid interactions, bed form and suspension, particle size distribution, combined wave current flow visualization, image processing, dispersion. So lot of work had been done by the sir. If I talk about the educational qualification, sir has done his MSc from IIT Kharagpur, then DIIT, post MSc from the IIT Kharagpur, PhD also, and postdoctoral fellow from ISI Kolkata. And sir has various positions at ISI Kolkata, like starting from the fellow, visiting fellow, lecturer, associate professor, professor, head honorary visiting professor, honorary professor, and sir is involved in various activities like visiting scientist, guest fellow, research associate, guest scholar, visiting scientist at the Stanford University and University of Illinois, and visiting faculty in the year 2011 at King's College London, and successfully completed several research projects from ISI, DST, CSIR, NBHM, and DoD on the sedimentological fluid dynamics and digital imaging along with statistician and geologist. Sir has supervised 9 PhD awarded and 7 postdoctoral fellows, 10 project assistant, and several summer project students. At present, 2 PhD students are working and 2 postdoctoral students received a Fast Track Young Scientist Fellowship from the DST under his supervision in the Fluvial Mechanics Laboratory. Sir has a lot of awards in his list like GM Nathwala Award 2002 for the best paper in the Hydro 2002, ISH Pune Fellow Fish of Indian Society of Hydraulics ISH Pune, and many more. If I talk about the journal publications, then sir more than 130 peer-reviewed journal papers, more than 30 conference paper, and 2 book chapter and 4 book chapters, 2 book published, and 5 monographs. He is the reviewer of more than 30 journals, peer-reviewed journals, and if I talk about the projects, then mainly the title related to turbulent and incipient motion suspension, image processing techniques to study the particle behavior in the near wall region, experimental investigation on the genesis of the obstacle marks. So lot of things. Means the CV is very huge. It is having a very lot. I can't tell everything because it is. So I am not taking so much time, and I am directly inviting the sir, Dr. Vijay Mujumdar sir, for the keynote address. So I would like to welcome you, sir, for this in this FDP. Thank you for inviting our invitation.
Okay.
Yes,
Professor,
yes.
you have not said lot of things. It's not necessary even to say lot of things. Okay, it's a respected Professor Gachar, principal of the institute, and Kasia, Professor Kasia, HOD of Civil Engineering Department, and Professor R.K. Join. I know him very well for a long time. So, and Professor Nigam, Professor Dikrit. So, this is really, they have invited me to give a keynote lecture, and that's okay. But it's really great pleasure for me. Can you hear me? Hello.
Yes,
Can you
completely
hear?
audible, sir. Completely audible.
Can you hear me?
Yes, yes.
Okay.
Yes, sir.
That's very fine, great. Okay, it's a great pleasure for me to get an invitation from the institute, particularly Professor Rajesh Join. He has asked me to give the lecture on keynote lecture, but I am not that type person also to give the keynote lecture. That's okay, please. At the same time, and keynote lecture means I'm thinking to give something glimpse of turbulence and sediment transport. I know you people know some turbulence, also sediment transport, few things, I'm sure. But still, what I'm finding lot of things, problems, while I was just reviewing the papers of different countries, different places, I find immediately the most important thing is what is turbulence, basic things of turbulence. That is also problem difficult to, maybe I do not know, maybe the people know, but they are not writing those things properly. My feeling is because I do not know, maybe students are, most of the students are here, and also some junior faculties. I will be very glad to explain few things about the turbulence. Okay, you know that laminar flow and turbulent flow, these are most important two things in the fluid flow. And laminar flow is nothing but a just orderly movement, it is very smooth and orderly movement. And turbulent flow, if you go in contrast If you go like that, it's a completely irregular, erratic, and also something like random phenomena and chaotic, disorderly movement. So problem is coming here. If we the scientists to understand what is turbulence, then you have to go for the fluctuation or randomness, why it is like that. If you go for measurement something, at the same time, suppose if you have any measurement, then once you do the measurement, laminar flow, no problem, measurement only one, because it is smooth, you will get only U is equal to U. But problem is if you go for turbulence, then U is whatever you are getting instantaneous velocity, that U is the component of these two things. It's a decomposition. It's nothing. One is a U bar, that is the mean flow, and one is the fluctuation. And now if you go for U, V, and W, all three components, even pressure, all three components are the fluctuating components, and it's instantaneous component. These are the having fluctuation. Then if you go for U is equal to U bar plus U, what is U bar? U bar is a mean flow. Mean flow, if the U prime is, or V prime, W prime, P prime, if you get 0, what is then you are getting? U is equal to U bar. It is nothing but again you are going to the laminar flow. Once you are having the U bar, it is nothing but completely laminar type flow. So maybe high flow, no fluctuations or nothing. As I told you, in the laminar flow, no fluctuations and very smooth and very regular flow, orderly movement. That U bar, what you are getting, if you make the 0 U prime, V prime, W prime, you will get the U bar. That U bar is always again, you get that, that's a laminar type flow. But maybe this is high flow or something like. But because once we are getting the mean, so all other things, spikes or other things gone. Okay. Now if you go for laminar flow having some Navier-Stokes equation, you know that. And again, for turbulent flow, people are still having some question that turbulent flow, no equations are like that. But people are doing that using the Navier-Stokes equation in laminar flow, because as I say, in a laminar flow, only U is equal to U bar, same thing. But if you go for turbulent flow, it's equal to U bar plus U prime. And that U is nothing but components. There's two components, two things. Those U's, V, W, P, if you put in the Navier-Stokes equation, you will get a big equation. Those things, that is called Navier-Stokes equation, and Reynolds, that is called Reynolds stress equation. That means from Navier-Stokes equation to, we are going to convert, getting due to the fluctuations, we are getting the Reynolds stress equation. Okay. Now, if you go for Reynolds stress equation, that means some change is there from the Navier-Stokes equation. Navier-Stokes equation, we are only having the viscosity, but Navier-Stokes equation, you are having the viscosity plus other thing, what is called eddy viscosity. When you have any disturbance in the fluid, as I told you, I'm very simple way I am telling you, if the flow is there, very orderly flow, no question of disturbance. If you give some disturbance in that flow, you will get the completely chaotic phenomena. In that chaotic phenomena, you are getting U prime, V prime, W prime, P prime. And those things also involved in that Navier-Stokes equation. If you Navier-Stokes equation, if it is involved, you are getting the Reynolds stress equation. Again, at the same time, that means we know that is we know. Still, I am saying in the Navier-Stokes equation, 4 equations, 4 unknown. 4 equations. What are the 4 equations? 3 Navier-Stokes equation. 1 is a continuity equation. And so 3 equations, 4 equations, 4 unknown. What are the 4 equations? U, V, W, and P. And so that way is solvable. But we cannot solve it because it's completely, fully non-linear. Still, people are fighting to study the problem. Okay. Now, if we go for Reynolds stress equation, now you can see again we are getting 4 equations, but we have the number of variables, number of unknowns. 4 equations, unknowns, variable. And so like U, V, W, and P, exactly, you will get similar type of things also in the Reynolds stress equation. U bar, V bar, P bar, W bar plus other, the four things will be there, plus other 9 components you are getting. What are those things? You know the Reynolds stress. There's a Reynolds stress on stress tensor is there. The sigma x, sigma y, sigma z, and tau x, y, tau x, z. This way you are getting 9 components. That means 3 by 3 matrix you are getting. And somehow we can make some simplification of this thing. Then ultimately, out of 9, we can have only 6 components. So 6 components, that means 3 normal stress and 3 shear stress. That means xy, yx is the same. Xz, zy. You say that way, it is symmetry, it is probed. So we can think about the 6 components in the Reynolds stress equation, and that way plus 4 components. Then how many unknown we are getting? 10 unknowns. But we are having 4 equations. Absolutely impossible. But still the people are working on this. How? Now, to unknown those things, too much non-linearity. Now, 6 unknown equals 6 unknown variables. That means 3 normal stresses and 3 shear stresses. Those 6 to get the known thing, how it is possible. So you have to have the closed form solution. That is also due to Pendleton mixing length theory. People they are doing like that. So this is that way they are using. So some simplification, not completely things. Some closed form solution. What is that closed form solution? It means whatever it is there, you can make some problem solutions. It will be easy solution. Okay. These are the things now. At a glance, I am telling you about the turbulence thing. Now, question is, if you consider the only fluctuating components, that means U, V, U bar, U prime, V prime, W prime, P prime. Now, question of once upon a time, nobody could measure those fluctuations. Now we can measure those fluctuations. Even Professor Garde was there at that time. We are very lucky that we don't have him. And Professor Garde at that time, he was very happy to see that acoustic Doppler velocimeter. We got it in our institute at Indian Statistical Institute. That is 1999. That means 2000. During that time, we got the acoustic Doppler velocity. We did not know how to even I should not say like that, but it's difficult to say that nobody has there in India. And that I got it at that time, 1999. So from that time, we are working on that. And that, but how to measure this prime, the velocity? Because nowadays, all people, mostly all institutes, they are having this type of instrument, acoustic Doppler velocimeter, then LDA, laser Doppler anemometer, then PIV, then particle image velocimetry. A lot of people now, they are having this type of things. But problem is how they are measuring. Suppose you have the flow. You have the flow in a channel, in or flume. Professor John, can you hear me? Hello? Hello?
Yes, sir.
Can you hear?
Completely audible.
Can you hear me?
Yes, audible.
Oh, okay. Just I was asking that. Can you follow me?
Yes, I am following, sir.
What about the students also? They can follow other fellows, other
Yes, you can
professors.
call
Yes,
any
sir.
student by name, sir.
Yes, sir.
Okay. But if you can follow, fine,
Yes.
no problem.
Yes, sir.
And
Yes,
so
sir.
I'm continuing these things. Now
Yes.
I will show how to measure. When you will say the equilibrium state of the fluctuations. Okay. Now suppose in a channel, flume, you have started the flume. Now water is coming from the tank. Then slowly it is moving through the flume. But once you start if you think that if you will do the experiment, once you start the experiment, you go for water full of completely full that flume, then you start the pump for movement of the water. But here is the one thing. Once you start, immediately people are there going to measure the velocity. No, no way, no way. Mention the time, please. Then go for, suppose you have started that flume at 10 o'clock. Everything is fine in the 10 o'clock. You go up to the 11 o'clock so that it should be equilibrium state. But again, I'm telling some big word, equilibrium state. How you will see the equilibrium it has come or not. So that's thing. But again, why we need it? We have to do the fully developed flow, that in basic turbulence. What is that? Now, for the study of equilibrium state of the whether whole flume is okay or not, then you have to think that now you are thinking, okay, I will start measurement. Okay, go on starting measurement. How much you will measure and what is the sample rate? Those things you have to think. Suppose ADB nowadays 100 samples per second you can get 100 hertz, but we don't need those 100 hertz. Let us complete if you the work maybe 50 hertz or 40 hertz is okay. But yeah, that you can ask also me question that why not say 20 hertz? No, if you go for 20 hertz, you are missing. That means hertz means 1 second number of number of samples. Suppose 100 hertz means in 1 second 100 samples you are getting. If you go for 40 samples, 40 hertz, 40 samples. That means 1 by 60. So 1 by 40. That is the interval of time. That way you can think about. But as you closer and closer the interval, you will get the much more result. Okay, but how long it will continue, how much, then it is depending on the your measurement, depending on the flume, how much it is okay, stability state is come or not. That way you have to think, suppose you have started the 40 samples per second or 50 samples per second. At least you have to have 3 minutes to stop the sample. 3 minutes. Why 3 minutes? But we have studied, we have got a lot of questions from different places. You can think about to collect the data only 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, whatever you think you can do it, but time consuming. But again, then you have to check 1 minute data time series, find out the all mean, standard deviation, other things. 2 minutes, 3 minutes, 4 minutes. You see in which minute it is converging. Generally, 3 minutes is fine. 3 minutes sample collection with a 40 hertz per second, 40 samples per second, it is fine. Then you can see after 3 minutes, no change. So unnecessary, why should I go up to 5 minutes or 6 minutes? So if 3 minutes is okay, then fine, no problem. Then go on 3 minutes. Sometimes people are doing also 2 minutes, but they are saying, no, sir, I'm getting, why shall I go to up to 3 minutes? That is fine. If you can show, if you are satisfied, no question is there, because satisfaction is the most important thing. Okay, this is one. That means 2 things I have told you. You should start the measurement for after 1 hour. Then you can think this is the equilibrium state has come, because we have to measure, we have to do the fully developed flow. How to do it? Then collect the sample, start the collecting sample for, don't go once in your starting experiment, you can say, sir, this is the 3 minutes, okay. 3 minutes sample collection is fine, everything is converging. No, go on 3 minutes. Now question is, which place where you will collect the data in the flume? Suppose 20 meter long flume is upstream flow is coming, and then some guide vanes are there, then going on, then end of this tailgate is there. Which place you will collect the data? That is the most important. I am not saying any other thing, putting something. I am asking for the fully developed flow, no disturbance in the flow due to other object. So that way, but if it is 20 meter or something like, depending on the scale, after 3 meter, you can start the measurement. Each and every 50 centimeter. If you go on measurement up to the end, maybe 1 meter before the end or 2 meters before the end, you can stop and go on collecting data. You will see why you are collecting this type of longitudinal direction collecting data from the center of the channel, because of the to study the fully developed flow. Exactly. Without fluid double flow, you would experiment, whatever you do, advanced experiment or anything, completely useless. Rajesh, join. Can you hear me? Hello?
Yes, sir. Yes, sir.
Oh, can you hear?
Yes, completely.
Okay, good, good, good. So that way you can see fully developed flow. How we will do that again? I should say fully developed flow. How you will do it? Suppose from 3 meter to up to 4-5 meter, you have collected data. Now you check the data, plotting whether you are getting that, you know that in the center of the channel you will get the non-linear velocity, then you should get the log low. If you get that log low, suppose from one region from 4 meter or 5 meter to 8 meter or 10 meter, if you have the same velocity, same profile, then only we can say this is fully developed flow. Okay, what is the mathematical thinking of the free developed flow? What is this? That means you are collecting data, u velocity, u v w. Okay, if it is fully developed flow, vw should be zero, must be zero at the center. But if you go for u only, that u is you should give the log low or something non-linear type velocity. It should go from 5 meter to 10 meter. Then you can say this 5 meter region long, that is the fully developed flow. But again, why I am saying fully developed? Because u with respect to x is a constant. Velocity with respect to x distance is a constant. What it means? What is the equation of continuity from here? Del u by del x equal to 0. Is it all right?
Yes, sir.
Can you understand?
Yes, it would be better, sir, if you share your presentation, and then participant would be happy to see.
Now I will go for
Yes.
presentation. Okay. Now because I'm telling you is a log how to measurement, how to do the measurement. So that's fully developed flow. First important thing is the fully developed, to study the fully developed flow. How? From inlet. Inlet is difficult. Not inlet, no way you will get there. But little bit away, 2 meter away from the inlet, and outlet also 2 meter away. Within this region, it should be completely fully developed flow. Velocity function of x is a constant. Velocity is not depending on x. Velocity is with respect to x is a constant, and w v lateral velocity and particle velocity should be 0. Okay, these are the fully developed. These are most important things for studying any problem. If you go any advanced level problem, and at the same time you have to go for spectrum analysis, and you know Kolmogorov 5/3 law. If you follow that, then you can say you are having a fully developed flow, complete region of fully developed flow. Then you are happy. Okay. Now let's go. What I'm thinking, this is the turbulent flow. I have said something. Now suppose if you go for bed load sediment transport. So now suppose sediments are there in the bottom. Then sediment particles should move. How it moves? Velocity, it should exceed the critical shear stress. Critical shear stress means particle is there, some flow is there, or in all flow, particle will not move. But certain flow is there, in a particular flow is there, particle will start initiating the movement. That is the critical velocity. But when if you give the more velocity, then particle will go to suspension. Just think about this particle. Now, sediment transport is a very important problem in the river. If you go anywhere, you will get in the river, engineers. Now I can go to PowerPoint. Let's see. Can you see the PowerPoint? Hello? Hello?
Sir.
Hello?
No, sir.
Not
Can you
yet.
see?
Not yet.
Not yet?
Yes.
Oh, that I do not know. PowerPoint. Okay, I can see the slide rule. You see here, current. Okay. Can you see?
No. You can, have you shared, sir?
I shared it. Okay, let me see. I don't know. It's very difficult. Lot of things are having problem here. How can I? Okay, share. And is it, where should I go? Window or Chrome Lab? But you see, entire
Sir, window.
Window. Okay, if I
Yes,
go
sir.
to window, and again share is not coming. Share is the bottom is one share is there that is not highlighting.
Then you will have to click the entire screen. Okay, sir.
Now
Yes. Now it's
not.
It's not coming.
No.
No, it is not coming. Window is not. Now let's see. Now it is okay.
still not visible, sir.
You are selecting, sir, share screen and then select your computer screen. So whatever you will play on computer screen, we can see everything.
Share now. Share open share tray. This is up looking. Should I tray here? Should I click here? Then okay, sir. Okay. Now I'm in the desktop. So share screen. Screen share. Okay. Click. Now I clicked. Now it has come same thing earlier what I got. But same thing.
Sir, you have to click on the entire screen.
Now can you see? Can you see that? My
No,
hello?
sir.
Can you see?
No.
Oh, okay then. What is the problem?
Sir, can I show you by sharing my screen?
Huh? My?
Sir, I can show my screen.
Yes. No, it is not coming. Why is it share? Where is the problem? He is not highlighting anything in the share.
Oh.
Sir,
Okay, sir. What I can do? That is the big problem last time. But
Sir,
can you see?
what you
Tell
can
me.
do, you can send that presentation to mail us. We will just
Okay, sure. I can send it. I can
yes,
send
just send, please send.
it. Okay. I have to go to that mail. Okay. Rajesh, I'm sending to you.
Okay, sir.
Okay. And then reply.
प्रियांशु अभी ये भेज रहे हैं
Then,
सर है ना?
reply. Then, let me see whether I can. No, maybe stop. Okay. Wait. Hello? Huh? Yeah, mail I'm sending, it is going. Lecture note on bed load transport. It is going. Let's see, it will take Google Drive. Let's see whether it is going or not. It is a lot of things are there now. It's difficult to send. Okay, I am sending it now. Send. Is okay. Share with person. Got it? No. Share with one person view. One person. Someone needs to access to the file. So like what I should do? Turn link, share on. I am sending the PowerPoint. Already it is attached. Now it is going, not going. Cancel. Send. Okay, now it is, you should go. You should get it. Okay? This is sent. It will come. Rajesh join. It has come. Okay, you can show that. So what should I do now? Okay.
Sir, we can guide you from the sir can guide you from the WhatsApp call too.
WhatsApp call. Okay.
While doing a WhatsApp call, he can guide you to click the right button so that you can share your screen.
Why it is not going here? I don't understand. But you got it?
Yes, Sudhanshu is sharing your presentation, so just
Okay,
you can
sure.
speak on, and then you can ask him to next slide. Then he will switch to next.
Okay,
slide.
sure. You can show.
Sudhanshu, mail मिल गया ना? Hello.
Yes. Have you got it?
वो mail मिल गया नहीं क्या?
Is all right, Rajesh? Is it all right to you? Hello, Rajesh.
Wait for a minute, sir.
Sure.
मैं देख रहा हूँ, खुल रहा है अभी. डाउनलोड करना पड़ेगा ना पहले. ओपन विथ गूगल स्लाइड्स. 32 स्लाइड है बता रहे ना, तो उसको देखता हूँ मैं 1 मिनट. अभी खुल रहा है, प्रोसेसिंग कर रहा है. आपका माइक ऑन था इसलिए. हाँ नहीं, वो दोनों जगह ऑन था ना. तो इसको शेयर कर देता हूँ. आप मेरे को व्हाट्सएप कर दो. हाँ, तो ऐसा करता हूँ. तो एक सेव हुआ ये है ना. हाँ, वो इसको कंप्यूटर भी यार स्लो चल रहा है. डेस्कटॉप पर डाल दी. लगता है ये वो टीम चल रहा है ना, उसका. हाँ, उसको डेस्कटॉप पर डाल डेस्कटॉप पर डाल दूँ. ये है ही आ गया डेस्कटॉप पर. अच्छा, इसको कोई दिक्कत नहीं. डाउनलोड में आ गया ना. डाउनलोड से ही ले लो सीधा. व्हाट्सएप खुला ही है मेरा. कॉपी कर दो. आएगा गया ठीक चलो बोलता हूँ उनको yes we are sharing in few seconds just wait for a while
Okay, sure, sure. Can you see now? Can you see?
Yes.
Can you see the power presentation?
yes now it is visible sir
Presentation is visible?
yes yes
Okay. Okay.
so now you can start sir slides are visible
You see, but I cannot see the slides. It is showing my picture only.
Sir, I have shared from my side.
Huh.
You have I think pinned yourself. So you can pin Sudhanshu Dikshit. So I have shared, and you can tell for next. Then I will do next.
Okay, but problem is okay.
you can sir you can open your presentation on your PC
Okay, I can open.
yeah you can open but we will see your presentation from Sudhanshu so you can say next slide then you will do next slide
I have opened
okay
already.
so now you start speaking
Can you see?
yeah no we are seeing already you can start one by one slide number one slide number two like that
Okay, let me see. Wait. Yeah. Yes. Can you see the first slide? First slide.
yes
Okay. Now you see, as I discussed a lot of things to you earlier about the turbulence. Now you see the bed load. Again, it's just suddenly we have starting the bed load. Some you can see the video here, how the particles are moving in the river. Can you see it? Hello? Can you see
Yes,
this?
sir.
Okay.
Yes, sir.
Okay.
Yes, sir.
Now you see,
Yes.
left side is a video of how the particles are moving, and as a bed load and suspension and saltation, a lot of things are there going on. This is so much complex thing. And then see in the right side is in the river, how these gravels are there, boulders are there, and in between them there is some small channel is there. That channel is going on, flow is there with the sediments. And so that's back side, bottom side also some sediments. Now, if you go outside, then you can think about what kind of complex things are going on in the river. So that is you can think. Now you go for introduction. Backload and suspended load are the crucial parameters for the river engineering, channel hydrodynamics, and fluvial hydraulics. When the shear stress acting on the sediment particle exceeds the critical shear stress, that is the initiation of particle movement for defined processes of transport. Suppose, as I told you already, that flow, if the flow is there, particle may not move. If the flow in that type of flow is a bit higher, so particles can start movement. That movement is initial movement of that critical, that from that velocity you can find the shear stress. That is the critical shear stress of that particular movement. If it exceeds, the flow velocity exceeds the critical shear stress, then it will go to then it starts movement as well as in going to suspension in different process. So now you come to there are three modes are there for bed load. Bed load and suspension. See, is all that? Can you see? Can you hear me?
Yes,
Yes, sir.
Okay. Now three modes are for the bed load. Now you see the rolling, sliding, and saltation and jumping. Now you can see in this video, you can see what is rolling is going on, saltation is also going on. Then you see here, saltation is there, small particles jumping, and jumping, if it moves a little bit more turbulence fluctuation, then it will go to the suspension. It will not fall. Generally, it may fall long distance. So that is the thing. And now rolling, you understand from here. Sliding also you can understand. Sliding mostly it is happening in the smooth surface. If the particle starts moving, it will slide. And saltation, you understand saltation means jumping. These are the particles are jumping. Okay. Now bottom, just you go see the bottom figure.
Hello.
Yeah. See the bottom figure, rolling, sliding, saltation, and particle, or then the bed load. And these particles are in suspended load.
Yes.
When it goes on with the flow, the particles that goes on with the flow.
मोबाइल में टीम का ऐप पहले डाउनलोड करना पड़ेगा ना.
Can you see? Can you see?
Yes, sir.
Okay, good. Then the particle is at the same time in wash load also one thing. And particles are in suspension, it will move as long as, and it depending on suspension, when it will go for falling, it depending on the gravitational force or fluctuating velocity of the vertical velocity of the component. Okay. Now let's go. Now, bed load transport. Sediment movement is usually discontinuous. You understand these are completely discontinuous, and particle may roll or slide for some time, hold for a while, and again starts rolling, sliding. That means that particle moves intermittently. It means stopping, resting, they say, then again movement. These are called intermittent, irregularly over the bed as a contact process. Now, see, think about the wash load. As I told you, wash load is an important fraction of suspended sediment that is carried by the flow, and it always remains in suspension without any deposition. They don't have any deposition. That means dirty water, something like that. You can think about. Now we go for the bottom, some pictures. Now we come for what are the loads? Contact loads, saltation load, bed layer. Now, contact load and saltation load, you know, in the bed, the contact load, when the particles are moving with the sliding, so touching the bed, at the same time touching saltation, rolling, touching the bed, those type of contact, that is known as contact. Contact load is defined as the sediment particle moves sometimes by rolling, sometimes by sliding along the bed, and bed material movement dislodging with the bed. And now question is, saltation is also the same thing as I already explained. Now bed layer, what is bed layer? Near the boundary of the bed movement, the interface, bed as well as in the suspension, at that interface, bed load is nothing but a amount of material which are rolled, which are rolling, which are sliding, at the same time which are having saltation, height mostly about 2D or 3D of the size, 3D size. So these are definition of Einstein's definition, 2D, and depending on the what type of D in the bed. Now these are the bed load, and so here you can also see that's a particle in suspended load. Now bed load, amount of material carrying the flow, these are the bed load, and contact load and saltation load plus saltation load is nothing but a bed load. And suspension, amount of material which transported with the flow or by the flow as a state of suspension due to turbulent fluctuations. As I told you already, turbulent fluctuations I have discussed with you. And so U, V, U prime, V prime, W prime. But U prime, V prime is fine. But W prime is the most important fluctuating component to get the particles in suspension. As long as W prime is weaker, the particle will not, stronger and stronger, particle will not fall. And if it is weaker, particle slowly it will fall. Sometimes it will start the particle suspension from one place and it will go maybe 10-meter distance, it will go, then it will fall. It means that because the fluctuations, electrics are there, W prime, maybe initially it was very high and slow 10 meter up to that extent. W prime was high. So W, which is most important or responsible to get this particle in suspension, that particle strength of the W prime is going to decay. So that's why particle is going to down, so fall. So that means it is a gravitational force due to a completely gravitational force. Now you see low shear stress and higher shear stress. Low shear stress mostly bed load transportation, and higher shear stress mostly bed load, both bed load as well as in suspension. Now we go for wash load. As I told you already, total load. Total load is nothing but bed load, suspended load, and wash load. They're all things together is the total load. Okay. Now we go some small mathematical models. I'm just giving you idea. Some whatever the things I'm giving you now, only idea. So bed load transportation equations. You know that. Can you see here? Can you see here some figure? That figure, I think if you can remember from the Couette flow, you know Couette flow in the fluid flow boundary layer theory Couette flow, something like you see the linear type profile. That means bottom is 0 and topmost is a higher flow. It means some layer after layer sediments are there. That layer one after another layers are moving. How it is moving? This way. There, so it is moving. The first one moving, the second one, the third one. That way, ultimately it is 0. So Du Bois, he said, Du Bois, 1879. You understand? More than 100 years, about 150 years. So that way, he started the model to show the one kind of, I gave the query, it looks like Couette flow. That's why I'm giving like this idea. So QB is the bed load transport in weight per unit, N is the number of layers, and delta H is the thickness of each layer, delta V is the velocity of the each layer, and so, and this is the security. So say that way, I can show here. Now next. Now here, the model is like this. Model is, I'm not going to show the model. Model is something like this. Everything is, you see, shear stress, critical shear stress, and shear stress. So these are the bed shear stress is moving like this because we are trying to develop the model better. He tried to develop the model from the bed shear stress, that means at the bed load transportation. Okay. Now, next thing is important thing is that whatever the model you do or people did before Einstein, that is 1879, before Einstein did the 1950. Before that, all people, they did the work using the shear stress. But Einstein said no use of shear stress. Okay, let's go next. Einstein, okay, do not is the other model. These are the models, but all models, they are depending on the shear stress, bed shear stress. Okay, but now here also other model. Lot of models are there. Now Einstein bed load model. Now whatever I have discussed, these are the things shear stress concept. Now I will go for the probabilistic concept. Einstein's bed load equation is a completely probabilistic, but it is semi-empirical. But his idea is the most important idea, and a lot of people, they are working using this idea. What is that? It's a probabilistic idea, semi-empirical, supported by the experimental evidence, and derived from the probabilistic consideration. He opposed, now you see, he opposed the idea of the existence of critical shear stress. He said that what's the use of considering the shear stress or critical shear stress? Nothing. It can be explained. The bed shear stress is not bed load is not possible, or suspension is not possible using the shear stress. He said like that. Ultimately, he had a successful result. So, according to him, all particles of uniform sediment should start movement at a shear stress just exceeds the critical. If the critical shear stress exceeds only, then he assumed that sediment particle will start movement if the instantaneous hydrodynamic lift force exceeds the submerged weight. His conception is mostly the lift force and the weight force. No question of others. Lift force and weight force. If the hydrodynamic lift force exceeds the submerged weight force, then only it will be okay. It will move. Then once the particle starts movement, there is a probability of particle to be deposited at all points of the bed where the particles may not dislodge. And now the second point is, do you see, as the instantaneous leap force is random. Now again, everything is random. The way he is, as he's discussing the paper, he discussed the paper. If you go for turbulent flow is nothing but a completely random. Can you hear me?
Yes, sir.
Okay. Turbulent flow is completely random erratic phenomena. So once turbulent flow is random, using the turbulent flow, whatever you will get, everything you will get the random. Is it not? So everything you will get the random. Suppose due to the turbulent flow, jump is there, length of the particle is there, height is the movement of height, time of fly or halting, everything random, and rotation of the particle, once it goes to suspension, it rotates. That rotation also random. But those things, depending on randomness, how you are collecting data, you can show what type of distributions follow those parameters: jump, length, height, time, and rotation. These are all lift force. What type of parameter? What type of parameters they are? Which distribution follows? Lift force follows the normal type distribution. I'm sure you know the Elsamri and Einstein's paper 1945 or something like that. They said that lift force is a completely random as well as is a normal type distribution. Now you see, sometime I'm also taking considering my work. Once we did the image processing work, that image processing work, you know, that particles when go to suspension or in the bed load, and particles always rolling or rotation is there. Since rotation is there, that rotation, if we consider using the high speed camera, then we can see rotating force also, that's also random as well as the it shows the normal type distribution. Then at the same time, we studied that way why rotation is a random, why rotation is a normal type distribution. That means it's a depending on the lift force. It's a lift force. Lift force. Why the lift force is a normal type distribution? Because we got the rotation of the particle, rotating motion of the particle. We are getting the normal. So that way they connected the lift force as well as rotation. You know that, and then you go for consequently all parameters like jump, length, and height. These are the random. Do not consider the effect of bed form. But Einstein did not consider the bed form dynamics. He considered the bed form in the bed load. Now, experimental evidence, what is saying, a steady, intense, and here you can see he found that bed and bed load there is some intimate relationship between these two. Bed and bed load. Whatever the bed is there, what type of bed? Bed is nothing but it's just material. They are not moving that way if you consider. Now, if you start considering the bed movement, that means bed layer will be there, bed load will be there. And now, if you have the bed load or bed layer, bed, then there is some intimate relationship between the bed and the bed. A steady and intensive exchange of particle was observed between the moving bed load and the sediment load. The bed load moves slowly downstream. The motion of the individual particle is one quick step with a comparatively long intermediate rest period. So at the same time, when the particle starts movement, it will have a jump. That jump also, how far it will go, what is how and jump when it starts stopping, how long it will stop, and when it height, that means jump, height, everything will be the random phenomena. So that way, different transport rate can be achieved by using the average time between the two steps of the and thickness of the moving layer. So now physical model, I'm not going to explain it, it is a long, big thing. So what is the concept of the physical model? Bed load equation expresses, according to Einstein, an equilibrium condition of the exchange of bed particles between the bed layer and the sediment bed. There is some exchange of particle between the bed layer and the sediment bed and sediment bed. There is a exchange between these two, bed layer and sediment bed. Okay, then once this is there, this implies that number of particles deposited per unit time and per unit bed area must be equal to the number of particles eroded per unit time and per unit bed area. Whatever the particles are starting for the erosion, and it absolutely true, these things particles will be deposited. That way, he said, this implies that number of particles deposited per unit time, per unit bed area must be equal to the number of particles eroded per unit time and per unit bed area. That means some equilibrium state. That means this type of phenomena he used. That means erosion must be equal to the deposition. That type of probabilistic idea he used. In the erosion also he used the probabilistic idea, deposition also he used the probabilistic idea. Then combining these two together, he got a very, very good bed load equations model. So these are the mathematical things I'm not going to show. And these are the things. So that way, now if I go, now that means two conceptions are there. Most important thing, one is a shear stress concept, one is the probabilistic concept. Shear stress concept is a very, very long time back. Still we are working, but probabilistic concept is started by Einstein. Einstein is Hans Einstein, Albert Einstein's son. He was a physicist and as well as civil engineering. Okay. Now go for suspended load. Suspended load also is a conventionally regarded as a sediment particles and is surrounded by the fluid, and also it will stay in suspension for the time being, and maybe longer time being, whatever the time is, it will be deposited somewhere. The mechanism of suspension being transported by the flow is rather complex because exchange of both, because at the same time, what I can tell you, in suspension means is a very complex thing. Once it goes to suspension, again is a complex. Why? There is exchange of mass as well as momentum. Momentum equation, why it comes, is a Navier-Stokes equation or Reynolds-Stress equation, and why the mass is known as a diffusion equation. So diffusion equation and the momentum equation, when it's combined, so it is again a complicated thing. Okay. So next, then spreading of sediment particles in the flow in a random motion is known as diffusion. It has come now, diffusion. Now spreading of sediment particle in the flow by random motion is known as diffusion. At the same time, if I tell that about the diffusion, if you go on that fixed law, it has come from the fixed law. But while the motion due to the velocity is known as convection. Now you see, it has come from the fixed law. One-dimensional fixed law process is this. Suppose if you have a glass of water, can you hear me?
Yes, sir.
Okay. If you have a glass of water, stand still in glass of water, no stirring or anything. So if in that glass, if you without any stirring, you put a drop of dye, you will see after a certain time the completely glass of water will be dyed, or some color, different color, or if you put some salt, completely it should be salty, if fruits are sweet, if it will be completely it will be sugar, sweet, something like sugar. That way, if you think about that, what is how these are all from high density to low density, it is moving. So that is due to molecular agitation. So here you can see dm is the proportionality coefficient between molecular diffusion. Due to this molecular diffusion or molecular agitation, the particles are moving from one place to other place. So fluid flow is not there. Okay, in that fluid flow, if you consider the diffusion equation, this is the diffusion equation, equation 19, del C by del T, minus del Q by del X, dm del square C by del S square, diffusion equation. Now, if you go for velocity, but okay, if you, that diffusion equation again, it shows the normal distribution. If you have the velocity, then you see left side is a convection and right side is the diffusion. So then whatever you will find, that is now, again, now this is laminar diffusion coefficient. So that is the most important, again, laminar diffusion equation. If you go for turbulent, again you have to see C bar plus C prime, equal to U bar plus U prime. So that way you have to substitute these things to the equation 22. Then you will get the, now you see the one kind of equation, what is called is a turbulent diffusion equation. That is the source. Equation 24 is a turbulent diffusion equation. Left side is a completely laminar diffusion type, and right side is not the left side. And also this first, after first, second, third, fourth, up to fourth term laminar type, and up to fifth term, from the fifth, sixth, and seventh, these are the turbulent diffusion, and right side is completely laminar diffusion. Now, how will you get the turbulent diffusion equation? Again, that is nothing but what we call, is a difficult to know, study these things. Again, closed form solution. Suppose these are C prime, U prime bar, C prime, V prime bar, C prime, W prime bar. These are the completely unknown, and C is also unknown. But again, if you have only one equation, how you solve it? So that's why we need the closed form solution. If you go for a closed form solution, you will get this type. You see here, these things del C by del C. Can you see?
Yes, sir.
Okay.
Yes.
Good. Okay. Now you can see the minus delta C prime U prime bar is nothing but, we can, the closed form solution means this unknown equation, this unknown term can be regarded as a known type term, because C bar is this here. So if you complete, if you substitute these things, this thing here, then you can see at least gone, that non-linear terms gone. Now only we are having one equation, one unknown. Can be solved. Now you see, now again, once we are having this epsilon x, sx, epsilon sy, epsilon sj, these are again most important thing like eddy diffusivity, and these are the eddy diffusivity. Concentration from it has come from concentration, not something here. Now dm, this is molecular diffusivity, molecular diffusion. This is the eddy diffusion. But this molecular diffusion is much smaller than the eddy diffusion, because these having the very small magnitude, very small, maybe 10 to the power 4 or 5, but these are having the 10 to the power 1 or 2. So that way we can neglect this dm, we can neglect. Ultimately, we are getting an equation something like that. So this is a turbulent diffusion equation with this type of eddy diffusivity with respect to x, y, and z. Okay. Then you go for, suppose now this is the most important and very complicated equation, is difficult to solve. Now Hunter Rouse, what he did, Rouse equation, assuming the steady state condition del C by del T equal to 0, and no variation of concentration either in x direction or z direction. So that means these things are 0. So let's go to there. Hunter Rouse, what he did, Hunter Rouse, what he did, this is unsteady, this term gone, and this term also gone. So this term's gone, and it has come only this term. And so at the same time, this term's gone, this term's gone, this term's gone, so this term's gone, this term's gone. So this term only we are having. Now you see here, this is the equation. So it is a function of y only. That is one dimensional. So that way del C by del P, what is P? P is the particle component of the velocity. And del C by del Y, and this is the ADBC. Now if we consider for this, now ultimately we can write, if you go for integration, you can see this is the integration. And V is the particle velocity. Now considering the particle free velocity to the equal to the fall velocity of the sediment particle and replacing this by this, we can get this. This is the very important equation that is 1937 Hunter Rouse used. Okay, but if you go for using the river flow data or flume data, you can get some data results, but those results are about 200-300% error. But again, Professor Atal-Fdp-Ldce-Civil said, he told me even, he may be 200% error, but still Hunter Rouse gave one model, maybe it is 200% error. Still, you have to check these things when you do the work. Suspension. Anybody who wants to do the work in suspension work, you have to start from this equation. You have to check. You have to show how much deviation from this problem, whatever you are working. Okay, how much deviation from this problem, whatever you are doing. Suppose you are working very high level, advanced level, you are working fine, but you have to check how much deviation from this value. This is the classical type of problem. So Hunter Rouse equation is a very important equation to you. And now this is thing, and that how to solve epsilon s and v naught. And in two-dimensional channel flow, relative shear stress tau distribution is given by this. This is. So I need to solve this. So I need how to get it. We need the velocity, we need the shear stress. So that way we need these things. So in epsilon m, I got it, tau t by 4. That's it. Everything is given in the Prandtl mixing length theory. So then epsilon m is nothing but now it is more or less a known thing. So now we are getting the solution of that equation. This is the solution of this equation. Okay, that equation. 26 can be solved. Now, if we consider beta equal to 1, integrating 26 and replacing these things by this, and equation 30, this equation can be solved as this. But now, the solution, if you have the solution, but you have to show the data, the result. Now you see the data, result. Now, C by C naught, as you check, you see velocity increasing means now, if the velocity increasing, you see here, that means fall velocity high, particle velocity increasing, fall velocity is high, that very near the boundary, very near the bed, it will become. So that is the thing. So now, this is more or less I have ended here. Now, if you have any question, that my things is whatever I want to tell you, that there are basic things are there for the bad load movement. One is a critical and one is shear stress concept. One is the holistic concept. Now, if you go for particle suspension, how these particles are going to suspension, mostly depending on the velocity, much higher than the critical velocity, critical shear stress. So then you can get this suspension. Once you go in suspension, you can see the particles are falling, but depending on the particle velocity and the AD forces. That, but again, Professor Rajesh Join, I am sure he will explain all these things. What is AD source? AD. And so AD is the most important thing. These are the nothing but agglomerational particles, that vortex. Those vortices are there in the turbulent flow, completely turbulent flow involving the vortex. Nothing without this. Whatever the turbulent flow is there, vortices are there, eddies are there. Those eddies are most important or most responsible to get particles in suspension. That's all. Okay?
Yes,
okay?
sir.
Okay.
Yeah.
Now, if you have any question, you can ask me. Now,
I request all the participants, if you have any doubt regarding this, even our postgraduate students are also available. They can also raise a query if they have.
okay. Now, from the lecture, what I emphasize that first thing is how to develop the turbulent flow. How to measure the turbulent flow is the most important, and what is fully developed flow. How long you should consider to get the fully developed flow, how long you should consider to get the equilibrium state of the fluid flow. But in the fume, water is there, no problem. But you have to, because you are doing the experiments, because you are doing the control condition experiments. So everything in your hand, maybe time consuming factor, but you have to do the equilibrium state as long as you want, keeping the time. So maybe at least 1 hour and start the flume, at least 1 hour you have to keep, then go for measurement, define locations. You have to see whether location velocity profiles are same or not. If they're same, then it's fine. And what type of, how much you consider. And these are the things, one aspect of turbulent flow, and other things I've made the bed loads, suspension, and something like that. Okay. Thank you very much. That's all. Okay.
Yes,
Okay, sir. Sir, there are two questions.
Some questions?
Yeah.
Yes, yes.
Okay, please.
One is that, sir, can you tell me at what frequency the turbulent analysis can be studied perfectly using ADB data? Means what frequency we will take generally to measure the turbulence data. Some researchers are using 40 hertz or 50 hertz, while some are using 100 and 200 hertz using Noltec ADB.
Fine, fine. I already explained these things. Okay, I'm again. Suppose in your ADV, 100 hertz is there. That's fine. But because we don't need 100 hertz, because just we are not doing that type of turbulence. But if you want to do, you can do, no question.
Yes.
But generally, if you go for 25 hertz, if you go for 40 hertz, if you go for 50 hertz or 60 hertz, but depending on the fluctuations. They said, suppose if you go for 40 hertz, then go on 40 hertz, collect the sample, see the variation, how much it is changing, 40 hours and 50 hours. But as you go on more and more number of particles of 50 hours, that means why we are doing like this, suppose interval, if the interval of collecting the sample, suppose 40 hertz means 1 by 40 second part.
Yes.
That 1 by 40 in turbulent flow, 1 by 40 second is a very large time. It's also very large time. But sometimes you can miss the bursting phenomena. Ejection, sweeping, those type of things you can miss. If you go on 25 or 20 hertz, then you are completely missing everything. You will not get any result. Maybe you can get the result, these are erroneous results. So at least for you, the safety side, you have to be 40 to 50 hertz to get the whether to get this bursting phenomena, whether this interval can capture the bursting things or not. These are proved by Professor Mutlu Somer of the Technical University of Denmark. And we have also some papers there with him. And Fretso, they have studied a lot of papers on this. But at least he also told me that don't go below 40 or 50 hertz sample collection. Then you will miss the turbulent bursting. You can do the work, velocity, intensity, shear stress, that's fine. But if you go for higher and higher turbulence, so even if you go for turbulence production, turbulence kinetic energy, turbulence dissipation, you will completely miss. And if you go for only 40 hertz, then you can think about it. Still, the people are asking you should go more if you go for higher order turbulence.
Okay, sir.
Okay?
Yes.
Okay. At least you should take 40 hertz. That's okay. 40 hertz, 3 minutes for the sake of everything. 40 hertz, 3 minutes. Okay?
Okay, sir. So thank you so much, sir, for enlightening and
At the
giving a
same
very
time,
detailed note on the flow characteristics and turbulent statistics in annual channel, including all the types of loads, all the important equations, physical equations, models, Rao's equations, and that generally we are using in the analysis of turbulence. So thank you all, sir. Thank you so much.
Thank you very much. Thank you very much. And I'm receiving great pleasure that you invited me, but it will be some problem on that showing that video. That's okay. Okay. Thank you very much.
Yes, sir. Thank you.
Yes.
Thank you for joining and thank you for sharing your
Thank you,
experience.
sir.
Okay, okay, good. Good, thank you. Thank you very much. Okay. If you have any question, please let me know. Okay,
Yes.
sir? Yes.
Sir, at present there are no questions, but if we have any question, then we will share with the mail to you,
Yeah. Sure,
so that
sure,
we will,
sure.
yes,
Professor. Sure, Professor
that,
Rajesh, join. It's no problem, no problem. Sometimes if you want that fully developed flow, how do you measure? How do you get the fully developed flow? Because everywhere people they are asking, whenever we are sending the paper, they are asking for how do you measure the U star value, kappa value. Those are the things always they are asking. At the same time, when I review the paper, same thing, they are not using anything. So these are the difficulties. I'm thinking that also in basic turbulence, you must understand the things. Okay? Hello?
Yes, sir.
yes,
Yes, sir.
Yes, okay.
okay, sir.
Thank you very much.
Thank you, sir.
Yes, yes, thank you so much.
Now I
So
will.
now we are closing this keynote address,
Okay.
and we will have a break of half an hour, and then we will join around 2 p.m. Okay, for the second session. So thank
Okay.
you all. We will meet again at 2 p.m. Thank you so much, sir.
Thank you. Thank you. Thank you very much, Professor Rajesh. Okay.
Yes, sir.